Hello, we are going to discuss this electron nuclear hyperfine interaction.
I introduced this last time
Without explaining what it means. So, today we are going to figure out what it is. Electron nuclear hyperfine interaction. I said that this interaction produces lots of hyperfine lines, and let us try to understand the origin of that. So, for that let us take the simplest possible system you can think of, which is free radical, is an hydrogen atom. It has one electron, of course, and one proton. So, what we have discussed so far, if I try to look at the energy level diagram of this in a given magnetic field, for the electron I get a splitting of this kind, which is the electron Zeeman splitting, corresponding to the electron spin. Let us call it S of ms equal to minus half, and here ms equal to plus half. And as we discussed earlier, if this is the case, then I see a transition which looks like this, delta E is equal to B, and this will be equal to h nu. So, for a fixed frequency experiment, the Epr spectrum will look like, I will draw it here. And this is the magnetic field. So, this corresponds to the energy of transition which satisfies this relationship. But what it is found that if the experiment is done, this spectrum does not look like this, but it appears to be this type of thing. As a function of magnetic field, it gives one line here, another line there, and with respect to center, there is no line exactly at the middle of that. And so, this line, Epr line, is split into two in case of hydrogen atom. So, we call them, of course, the hyperfine line of hydrogen atom. By the way, this gap is actually almost 506 Gauss or so, approximately, quite a large splitting. What is happening there? Why does hydrogen atom give two lines and not one as you expected from this side of thing? So, one simplest way to look at it is that this is probably not the complete energy level diagram of hydrogen atom, something else is happening. So, if I get two lines, naturally there will be two transitions involved there. What is the origin of that? Try to look at it. There is electron there and a proton there. Proton also has a magnetic moment. So, in a magnetic field, this will also align according to its nuclear spin state, which is I equal to half, mi equal to plus minus half. So, it will be either along the magnetic field or opposite direction. Now, the electron which is present there in the atom, it finds itself in the presence of two magnetic field. One is the external magnetic field that is applied by the spectrometer, and second one is the local magnetic field the proton produces. Now, you see that there are two remnant of the proton spin. So, that means the local magnetic field that the proton produces either adds to the external field or it subtracts the external magnetic field. So, depending upon therefore the proton spin state, this energy level is going to split now. So, here suppose it appears this way, that this splits into 2, similar this will also split into 2 depending upon the what nuclear spin is associated with the electron spin of -half. So, this could be now ms equal to -half and m of I equal to plus half, let us say. This could be ms equal to -half and mi could be will also be -half. Remember that electron Zeeman interaction is much stronger than the nuclear Zeeman interaction. But here we are not looking at the electron Zeeman interaction, but it is the interaction of the electron magnetic moment interacting with the nuclear magnetic moment. So, the splitting is given by this. Similarly, here ms equal to -half and mi equal to sorry ms equal to plus half and mi equal to -half, and this will be ms equal to plus half and ms equal to plus half there. So, why this arrangement is of this kind, that we will see again later, very soon in fact, but let us take it to be true. Now, there are 4 energy levels now, where earlier we had 2. And Epr spectroscopy, it is the electron spin which changes, nuclear spin does not. NMR spectroscopy, it is the nuclear spin that changes, not the electron spin. So, here if we draw the line correspondingly without flipping the nuclear spin, you see that one transition will go from here to there, ms equal to -half to plus half, mi remains plus half and plus half. Here another one, ms equal to -half to plus half, mi remains same and -half and -half. So, you see the 2 transitions corresponds to 2 different energies, and that will be reflected here in 2 different types of magnetic field. So, the splitting that you see here is therefore coming from this possible orientation of the nuclear spin in a magnetic field. See, in one proton I get possible orientations of 2 types, I get 2 lines of this kind. So, I get 2 lines here, and these are called therefore hyperfine lines coming from the one proton. Whose spin I equal to half. Okay. Now, suppose I have got more than one such nuclei which has got spin halves. What could be the simplest example? For hydrogen atom, I can go to this hydrogen molecule ion. It has got 2 protons, and they are identical in all respects. We call them 2 equivalent protons. So, we go through similar argument now, that in a magnetic field these 2 protons can align, let us say all of them can align this way, or this one can be up, other can be down, or this could be down, this could be up, or both could be down. These are the possible nuclear spin orientation in the magnetic field, and each of them give us to a local magnetic field that the electron will see. So, this energy level that I have drawn here will be modified in this fashion. I have got these two energy levels for now for this electron spin of minus half, these are the possible nuclear spin. So, this will split into this. Now, imagine here the electron's nuclear spin of 1 is opposite to nuclear second one. So, net local magnetic field due to this combination will be 0. Here it will be higher, this will be lower, or this will be lower, or this could be higher. So, let us write in this fashion that this will be total spin of nuclei could be plus half minus half, this will be, these are the possible my component there. Similarly here, okay, the electron spin is plus half. This will also have three types of nuclear spin arrangement. So, I write in this way. So, I can draw the splitting of the energy levels due to the nuclei could be drawn in this fashion, that this is split into 3. So, this energy level also split into 3. Now, we follow the same convention earlier, that when the electron paramagnetic resonance transition takes place, nuclear spin do not change, electron spin does. So, transition from this to this, one possibility. Another possibility is from this to this, the third one is from this to this. And you see that since the energy gaps are different, so they will appear at different magnetic field. But the middle one is exactly the same as here, because the nuclear spins are just opposite to each other. So, that does not contribute to any change in the local magnetic field. So, this spectrum therefore, if I have to, what we predict from here is that Epr spectrum of this hydrogen molecule ion should look like this. As a function of magnetic field, this will look like true. This is the way, but this is not quite true. The three lines of equal intensity that comes from this sort of argument is not quite true. The reason is that, see, the number of possible allowed nuclear configuration is of this kind. So, even though there are 3 energy levels, you see that number of molecules that will appear here will be, I said 2 of them there, similarly 2 of them there, because the first proton spin could be up, second could be down, or first could be down, second could be up, both are equally likely. So, in a sense there are, you may either call it the 2 energy levels are there which are degenerate, or the number of particles that are distributed here will be such that there will be twice the number of particles here compared to this and this. So, the intensity of the Epr line will be twice now, this kind. So, this is, if I expect 1 is to 2 is to 1 type of intensity for this system there. What we had here, that these 4 energy levels are there, all levels are almost equally likely. So, intensity of number of particles that this molecule transition will be seen, and number of molecules that this transition will be seen will be exactly equal. This will be 1:1. So, you see how therefore the relative intensity change as the number of nuclei which are producing the splitting change. Here both are spin half systems, so I get a splitting of 1:2:1. Now, here I could therefore take the example that I showed last time, is that this 2,5 ditersibutol semiquinone anion radical gives a spectrum which in actually intensity is 1:2:1 type of thing. And the origin of this now could be easy to visualize. You see one proton is here, another proton is here, and they are equivalent in all respects. So, I can have argument of this kind. The way this nuclear spins of these two protons are aligned gives rise to this sort of spectrum with intensity 1:2:1. It also shows a lot of other things, is that electron, though we draw here in the structure, electron is sitting here, but that is only the crudest possible picture.
The unpaired electron is present throughout the pi cloud of the benzene ring and interacting with all the ring protons. The Epr spectrum shows this.
So, in a sense, the measure of the splitting here or here is a measure of the strength of the interaction of the electron and the nucleus. So, we can continue further with this sort of argument that if I have got more than 2 spin half nuclei, what will be the corresponding Epr spectrum? Let us do one more and then we will generalize after that. Suppose we have a system of 3 protons and that is also a radical. Something I can think of is, let us say, methyl radical. These 3 protons are equivalent in all respect. So, I could draw similar energy level diagram as earlier. For electron, this is the ms equal to minus half and here ms equal to plus half. Now, we have got 3 protons and all of them will align in the magnetic field according to plus half or minus half each of them. So, I can get this sort of possible orientation. It could be up, 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 all 3 could be up, one possibility, or this will be up, down, up. Only 1 down, 2 ups, or it could be 2 down, 1 up. Or all 3 could be down. These are the possible nuclear spin in a magnetic field now. See here that each of them now gives rise to local magnetic field that the electron will see is different for all 4 of them. Maximum difference will be here, maximum here and minimum there, but nevertheless each of them will be appearing as a splitting of energy levels here. Now, so, what do we expect now, considering what we have discussed here? Each of these levels will be split into 4 lines now. So, it will be similar here. So, if we write the corresponding total Mi, the total nuclear spin, this becomes plus 3/2, this becomes plus half, this becomes minus half, this becomes minus 3/2. So, this will split, let us say it will be these are the possible values of the proton spin, total angular momentum, quantum number. Similarly, here this will be minus 3/2, minus half, plus half, plus 3/2. Now, the same argument as earlier, exactly same. The transition will be from the level 1 to the other level, which does not involve any change of the nuclear spin. So, that transition is here to here, other is from here to there, and then these 4 transitions are possible there. So, the Epr spectrum will consist of 4 lines, but will the intensity be equal? Certainly not. See, the way we had this 1:2:1 intensity ratios can be now extended to this number of possible arrangement for this and this is one type. If you say 1 unit, this will be thrice the number of molecule will be having this sort of nuclear spin configuration. This becomes 3, this also becomes 3, this becomes 1. So the Epr spectrum will therefore look like this function magnetic field. This will look like this. So with the intensity ratio of 1, 3, 3, 1. So it gives 4 hyperfine line, and the energy gap of this will be same as this, because the energy gap between this is same as between this and this, and that in turn comes from the magnetic field that this sort of arrangement of nuclear spin produces at the electron. So you can see now pattern now. Let us summarize now how we can get this various line, and then we will generalize it. So where electron, it gives one line spectrum, 1 spin half nucleus gives a splitting of this kind. So this is the center of this one. So this means it is splitting due to the one spin half nucleus. In our case, it is a proton. If you have 2 of them, then the splitting looks like this. So here it was 1:1, now 1, 2, 1. If I have got 3 spin half nuclei, then I get a splitting which looks like this, 1, 1, 3. So this sort of splitting that comes from the equivalent nuclei of spin half has certain pattern. These numbers are supposed to be familiar to some of you, is that they come from the binomial expansion of a plus b to the power n. If you do it, the binomial coefficients have exactly same number. So these numbers can be generated in form of triangle, we call Pascal triangle. Let us say I have got 1 here, then 1:1, then 1, 2, 1. See, then I have got 1, 3, 3, 1. The triangle is generated in this fashion that if we starting from 1, let us go one step below, I add the number which is directly the top left and top right. Take sum of these two, assuming there is 0 kept there. So here this plus this gives this number, 0 and 1 gives 1. Similarly here 1 and 0 gives 1. Go down, here again I add the numbers which are directly to the left and to the right. Imagine there is 0 there. So this 1 comes from the sum of this and this is 1. This 2 comes from the sum of this 1 and 1, 2. This comes 1, 1, 0 and 1 is 1 here. So with every step we just add the 2 numbers which is the left side and right hand side and add the 2 to get a number below that. So this triangle is called the Pascal triangle. Next one, same way, because here this is 0 there, gives 1, and this gives 3, and this gives 1, and this which is 0 gives 1, 3, 3, 1. We can therefore generalize that. So if I have got now 4 spin half nuclei, I can easily predict the spectrum which will look like from this Pascal triangle. It will be 1, add the 2, 4, this will be 6, add the 2, this will become 4, becomes 1. So This is the Pascal triangle. You can keep on generalizing this. So, this example is given here, we saw earlier, this one. This radical has 4 equivalent protons, they are equivalent in all respects. So, 4 equivalent proton gives rise to 5 lines as predicted by this generalization. But intensity ratio is 1, 4, 6, 4, 1. So, here if you measure carefully, this is almost equal to 1 is to 4 is to 6 is to 4 is to 1.
See how beautifully this agrees with our prediction.
So, this way we can predict the spectrum of more complicated radicals, and that sort of example and their interpretation we will take up later. And right now we just summarize that from the Epr spectrum, when you get lots of such hyperfine line, we can very easily characterize or even guess very intelligently the nature of the radical, what sort of nuclei which are present there, which can give rise to such hyperfine lines, and from there we can characterize it almost unambiguously what the radical that could be. So, before we close, we just take one more example which is somewhat different from spin half. This generalizes only for spin half nucleus. Suppose the nuclear spin is not half, it could be 1, carbon 13 spin half, but nitrogen 14 is spin 1. So, if what happens if the nuclear spin is 1, then I equal to 1 and its component Mi will be -1, 0, +1. So, in a magnetic field this nuclei will also orient in 3 possible directions, and it will produce local magnetic field which will be having 3 different values. This will not have no magnetic field. So, if I draw the hypothetically energy level diagram of one electron interacting with a nucleus of this kind, what do I see? First, the electron Zeeman splitting will look like this. This is the Ms equal to -half, Ms equal to +half. So, when this electron sees the presence of the nuclear spin, it will split into 3 energy levels, Mi equal to +1, 0, 1. This will split into 3, Mi equal to -1, 0, Mi equal to 1. And then based on this condition that when the Epr transition takes place, electron spin changes from -half to +half, but the nuclear spin do not change. So, that allows me to have these 3 transitions from 1 to here to here, here to here, and third one is from here to there. So, these 3 transitions will be reflected here in the spectrum. That earlier the spectrum was here when there was no electron nuclear interaction. Now, this is split into 3 because of these 3 energy levels here. So, I get transition which looks like this. One is exactly below the other because this energy level is same as that is here. What about the intensity ratio? You see that each of these 3 levels have exactly equal population, 1:1:1. Here also 1:1:1. So, that will be reflected in the intensity of this will also be 1:1:1. So, if the total nuclear spin is 1, here I get 3 levels. Compare that with H2 type of system, whereas the total nuclear spin was 1, but they were coming from 2 protons of Mi equal to half and half, or -half or +half, or -half or -half. So, these are giving rise to 1 is 0 -1, which is very similar to this. But here the Epr spectrum looked like this, that I got 1:2:1, but on the other hand here we have got 1:1:1. The reason is again obvious that here this transition involved energy levels were twice the number of particles that could stay here, but here all the levels have just same number of particles. So, I get 1:1:1 here, 1:2:1. This also shows the power of Epr spectroscopy, that by knowing the not only the number of lines and also the pattern of relative intensities, I can guess very accurately the type of nuclei which are causing the splitting. If I say 1:2:1, I will most certainly be able to say that 2 spin half nuclei are causing the splitting. I may not be able to say that it is coming from the 2 protons if I do not know the chemical nature of that, but the fact that I see this intensity ratio, that they must come from the 2 spin half nuclei. Similarly, if I see a pattern of this kind 1:1:1, I can most certainly say that this comes from the nucleus whose spin is 1. It may be nitrogen 15, I am sorry, nitrogen 14, but unless I know the chemical nature, I will not be able to say that. So, the example of that is given here, this one. Here, if you see that this free radical center O dot is near a nitrogen, this nitrogen nuclear spin is 14. So, that is exactly what we have discussed here, and we predict that the intensity will be 1:1:1, and that is what is seen here. So, with this we stop our discussion of the hyperfine interaction, and later we will continue to find the origin of this interaction.